13, properties of solutions. Okay, so we learned last year, earlier this year, that a solution, that word solution, is just another name for what?
A homogeneous mixture.
Homogeneous mixture. Okay? Homogeneous mixture is a solution. Okay. We're out of class now? Just saying.
You're live.
Okay. I know I am. All right. Now, homogeneous means what?
All together. It's everything's mixed thoroughly.
No.
Can't see through it.
No.
You can see through it. Right, you can see.
Homogeneous mixture.
It's
The
incorporated all
particles are
together.
dissolved.
One at a time.
The particles are fully dissolved throughout.
It's close.
You can't see all the different parts that are in there.
Okay, so the phases are uniform throughout. Okay. The opposite of a homogeneous mixture would be a heterogeneous mixture. So an example of a heterogeneous mixture would be like dirt in water. I can see the dirt in the water. It's heterogeneous. I can see the different phases. I can see the solid and I can see the liquid. A homogeneous mixture says, I can't see the different phases. It looks the same all the way throughout. Okay? It looks the same. I'm not going to see any solids in there or any gases in there and that sort of thing. It's going to be uniform all the way through. Okay? And actually, look, it says it right here. In a solution, okay, the solute, that's the stuff you're dissolving. Okay? Is dispersed uniformly through the solvent. The solvent is what we're dissolving the stuff in, or the dissolving medium. Okay? So far we know what a homogeneous mixture is, and we know what a solute is, and we know what a solvent is. So if I'm making Kool-Aid, water would be the solvent. The sugar would be the solute. The Kool-Aid mix would be the solute. Okay. Now, you can have substances that are in different states forming a solution. So let's take a look down here at the examples that they give. Okay. So the first example is if I put a gas and a gas together and I mix them, my solution is going to be a gas. And the example of that is the air in the room that we're breathing right now. Okay? So in the air, what gases are present? Oxygen, nitrogen, little tiny bit of CO2, and some xenon, possibly a little bit of noble gases. Okay? So that's a mixture of gases. Okay? And the solution itself would be a gas. Okay, so, I'm sorry, the state of the solution would be a gas. So we would consider this air to be a solution. It's a homogeneous mixture. Okay? Another example that we're given here is a liquid solvent and a gas dissolved in it. So it says oxygen and water, okay? And in that case, the solvent is a liquid, which means the state of the solution is also going to be a liquid, okay? Now the next one here is the one that I wanted to talk about, which is liquid and a liquid, okay? Alcohol and mixed with water, for example. So if we have a liquid and a liquid, or even a gas and a gas, which one would you consider to be a solvent and which would be considered the solute?
The bigger one.
The what?
The solvent, the one with more mass.
The one that you have more of, okay? So if you have more water, then the water would be the solvent, and the alcohol would be the solute. So whichever you have more of is going to be considered the solute. solvent. Okay? Any questions? Okay. So, what we're looking at here is, what's all over this? Water molecules. Water molecules. Okay. And this is supposed to be representative of an ionic compound.
Make it salt.
Okay. Okay, we'll make it sodium chloride.
Cute.
Whoops. Okay. Now, if you're going to put salt into water, in order for it to dissolve, a couple of things have to happen. Okay? First of all, these water molecules need to move away from each other. Do they like to move away from each other? No. What's keeping them together?
Hydrogen bonds.
Hydrogen bonds. Okay? So in order to dissolve something in water, we have to have the water be more attracted to that substance than it would be to another water molecule. Okay? We've got to separate those hydrogen bonds and let those water molecules move apart. And when those water molecules move apart, then they are going to be attracted to the different ions that are in the salt. Okay? So then, let's see. If this is sodium chloride, would the green be the sodium or the chlorine? The green is bigger.
The chlorine,
It would be the chlorine. Why?
because it has more electrons.
Because it gained an electron, so it's a little bit bigger than the sodium cation. Okay, so this chloride ion then is going to be attracted to what part of the water molecule? The hydrogen end, because the hydrogen end's the positive end of that polar molecule. Okay, so the water molecules need to move apart. The hydrogen end, the positive end of the water molecule, is going to be attracted to the negative ion and pull it away from the sodium that it's attracted to. And the negative end of the water molecule is going to be attracted to the positive ion, okay, and pull that away from the chlorine. And that's what has to happen in order for that substance to dissolve, okay? So, intermolecular forces between solute and solvent must be strong enough to compete with those between the solute particles, okay? The solute in this case is the NaCl, and between those in the solvent particles, which is the H2O, okay? Any questions on that? We good? Okay, how does the solution form? Well, I think I basically just went through that, okay? First we have the solvent, which in this case is going to be what? The water, okay? Pull the particles apart and then surrounds them, meaning the sodium and the chloride ions, okay? And the word we use for that is it solvates them, okay? So here you have the sodium chloride in the water. Here you have the water starting to solvate the sodium and the chloride ions, okay, until we completely dissolve the solution. I know, who would think all this is going on, right?
Zombie attack.
Okay. All right. How does the solution form? If an ionic salt is soluble in water, it's because what kind of intermolecular forces do we have here? Ion dipole. Okay, the dipole is coming from the water, and then of course the ion is the ionic compound, are strong enough to overcome the lattice energy of the salt crystal. Do you remember what lattice energy is? Yeah, basically the amount of energy to pull the ions apart in the crystal, okay, in the salt. And this is just a graphic representation of what I said before. You've got the slightly negative end of the water molecule being attracted to the sodium, and you've got the slightly positive end of the water molecule where the hydrogen is being attracted to the chlorine. Okay. Okay. All right. So, energy changes take place in order for this to happen. You'd never think this was happening if you were just putting like sugar in your tea, but it is, okay? So it's going to take energy to separate the particles. First of all, it's going to take energy to move those water molecules apart, and it's going to take energy to move the sodium away from the chloride ions, okay? So the solute particles, the NaCl, they have to move away from each other. And then the solvent particles, the H2Os, they need to move away from each other. And then when new interactions form between the water and the sodium, or the water and the chloride ions, I should say, then energy is released. Okay? And of course, this would be an endothermic or an exothermic process is going to depend on how much energy did it take to separate anything versus how much energy is given off when the new attractions happen. Okay? All right, and the enthalpy change for the whole process is going to depend on the delta H for each of the steps. Kind of very similar to what we did in the last chapter with the heating curve. We had to look at each step individually, and then to get the overall delta H for that process, we just added all the delta H's together. So this is looking kind of at the same thing, okay? We start out with the solvent, the water, and the solute, the sodium chloride. The first delta H here, change in enthalpy, is going to be the energy that goes into moving the water molecules apart. I'm sorry, moving the sodium and chloride ions apart. So, actually both. Okay? All right. Then the second energy change is going to happen or cause the water molecules moving apart and the sodium and chloride ions moving apart, okay? And then as the solution is formed, then energy is given off. That's our third delta H, okay? And so when we add all of those together, obviously, if energy is going into this happening, then delta H would be what? Positive or negative number? Positive, right? If energy's going into it, it's endothermic, okay? This delta H is going to be also positive, okay, because energy is going into it. And then this delta H is going to be negative, okay? This is the energy that's being released as the new attractions form and the substance becomes solvated, okay? So if the energy released is greater than the energy that went into the system, then this would be an exothermic process. And the opposite, of course, is true as well. Okay? All right. Why do endothermal processes occur?